Hello. In this video, we are going to continue with the gravitational series, and in that, as far as the potential that we were discussing about is concerned, we were to determine the potential due to a solid sphere, that is the mass distributed over the entire volume. So all we need to consider is a uniform solid sphere. And in case of the uniform solid sphere, we wish to determine the gravitational potential at different points uh, outside as well as inside, so as to speak precisely. And so this is the sphere, a solid sphere where the mass is distributed uniformly over its entire volume. And in order that we obtain the gravitational potential at any point, so as to speak, at a distance r from the center of the sphere, and let that distance be r, whereas the sphere has probably a radius of let's say a. Now, in order that this happens, or this is calculated, what we must know is that the distribution of mass, obviously the mass is distributed over the entire volume, and so we have mass distributed over 4 by 3 pi a cube. And the entire mass, because the spherical uh, object, in this case the entire mass, it's a uniform sphere, and sphere is a regular shaped object. So in case of regular shaped objects, what we have is that the mass can be considered to be just to be concentrated exactly as the center, that is the center of mass, where all the entire mass of the body can be considered, and from that it becomes easier. However, let's see whether our consideration is correct or not. Well, if we will just about integrate this. Now, in order that we integrate this, we need to have uh, an elementary volume. So let us consider an elementary volume. So this is an elementary volume in the form of a spherical shell. Although it looks like a ring, but obviously we have considered a sphere in three-dimensional case, and that is why this is the distance over here is r, and this is a spherical shell that we have considered. And let us suppose that this is lying at a distance x from the center, which is at the point O, and the thickness of the shell is dx. The thickness of the shell is dx. So with that thickness available to, let me write that clearly for you. So this thickness is simply dx. Now with that thickness available, what we can obtain is the volume of that shell. The volume of that shell, if you cut it open, the area that we are going to find, the surface area, is obviously 4 pi x squared, and the thickness being dx is simply multiplied to give us 4 pi x squared dx. Now this mass is distributed over this entire volume, so a unit volume will have a mass divided by 4 by 3 pi a cube. And what about this volume? Now this volume will obviously have a mass, let us say dm, and that will be equal to simply mass per unit volume, which is obviously the density, multiplied with 4 pi x squared dx, and the 4 pi's can get cancelled out, and what we are left with is 3m divided by a cube x squared dx. This is what the mass will be. And for any point which is due to this shell, obviously you have the because in the previous video we had discussed about the potential associated with the shell for x, that is the distance, being less than r. For x being less than r, we simply have dv to be equal to minus g dm divided by r. And as far as x being greater than r is concerned, we have dv to be equal to minus g dm divided by x. Now, if we are to determine the potential for an external point, and in case of the external point, what we can have is this one. That is the condition dv is equal to minus g dm divided by r. So for any external point which is lying outside the sphere, we have dv to be that. So we have v for an external point. We have dv to be equal to minus g dm divided by r, and so v is simply equal to the integration of dv, and that is equal to minus g. The r can go outside. It's chosen as per it's a chosen distance. It does not vary, and all that varies is the mass over there. And obviously if you are integrating over the entire mass, then all you are going to get is the complete mass, that is m, because the integration here will be right from the center till the very end, that is the till the surface. So obviously you are going to cover the entire mass in this case. What it tells us is that if the point is outside, the potential at that point is completely due to the entire mass, which is distributed uniformly over the entire volume, which also means that the entire mass has been or can be considered right at the center, which is what I had mentioned right at the beginning of the video, or at the beginning of this portion that I was about to discuss. Now this is for an external point. Now what about the internal point? Now in case of an internal point, we will have to take a few considerations. I'll redraw that sphere for you. This is more or less the sphere, and this is the center of the sphere. And what we do over here is that if we are to determine the potential, let us say at any point P, which is obviously lying at a distance r. Here r is an internal point as opposed to r being the external point in the previous figure. So this is a shell, somewhat I have imagined an imaginary shell, which on whose surface the point P lies, and the radius obviously is a for this entire sphere. We again consider a shell of thickness dx in order that we are able to measure this potential by every bit. So we again consider this spherical shell, and if you remember, just in the diagram that I've done above, we have the spherical shell, and again we are considering it to be at a distance x from the center. So this is at a distance x from the center, and the thickness, as in the previous case, the thickness is dx. So obviously the mass, now there will be two regions what we will be considering. There will be a region 1 where which is of radius r, and there will be a region 2 which is of radius greater than r. what we are about to do is that we'll be obtaining the potential for the region 1, that is of radius r, region 1 of radius r. R is the distance of the point from the center, point where we are to obtain the gravitational potential. And then we'll have the region 2. Now the region 2 is obviously the region which is greater than r. Now greater than r, but here greater than r where r is the internal point. There greater, you may be confused with this greater than r or something like that. Okay, but this is for the internal point, right? So what we are about to do is that we'll be considering the region 2, and for that firstly we will be obtaining it for the region 1. Well, what about the region 1? The region 1 has a mass, let us say m dash, and that mass will be equal to the mass per unit volume, which is 4 by 3 pi a cube, multiplied with the volume of the region 1, which is equal to 4 by 3 pi r cube. So 4 by 3 pi, 4 by 3 pi cancels out. All we are left with is m r cube divided by a cube. This is the mass which is contained within that region 1, and for that the potential will be simply, let us say, V1, which is equal to G minus because of the potential due to this gravitational force. So minus gm dash divided by r, because r is the distance from the center. So for that v1 is equal to minus g, instead of m dash we can use the values r cube divided by a cube. Obviously there was a r over there, so one of the r can get cancelled out. We are left with r square. So all we have over here is minus gm multiplied with r square divided by a cube. So this is the potential due to that region 1 which has a radius of r. What about the region which has a radius greater than r? Well, we simply obtain the mass over there, and then we calculate we integrate the mass from the value r, that is over there, from r to the end of it, that is up to the radius a, that is the radius for the complete sphere. So let's get to the other page. So the value of dm here will be the same as that we had obtained in the previous case, that is in case of the external point, when we were determining the potential at the external point for the sphere, because we have the distance of that shell to be at a distance x, and we have taken the thickness to be dx. So it will be having a mass dm, where dm, obviously by now you will be knowing the value, so I am not really going into the detail of it. So this is simply 3. If you can just go back to the other page, we have it over here. Where is it now? It's right there. Yes, this one. 3 mx squared dx divided by, well, there we had it as a cube. Here also we'll be having it as a cube. It is the same sphere. So 3 m x squared dx divided by a cube. So this is the mass of that elementary shell that we have considered, and the potential obviously is a minus gm divided by x. So dv2, that is the potential for the outer region, is minus g dm divided by x, and just putting the value over there for dm, what we get is minus 3 can go out, g remains as it is. Instead of dm, you have the 3 has gone through the other side, and m x squared dx divided by and there was one x over here and a cube, so one of the x can get cancelled out. You have x dx. Now this is to be integrated in order to find v2. So v2 will obviously be equal to the integration of this, so minus 3gm divided by a cube, a being constant, that is the radius of the sphere that has been given. Only thing that is changing or varying is x. And how does x vary? X varies the uh, from the radius of that point, or that from the point P, position of that point P, and then further outwardly till the surface that is having a radius a for that given sphere. So what happened over here is that we just obtained it for the entire region. Firstly, we obtained it for the region 1, and secondly, we obtained it for the region 2. And so with this integration, uh, we can obtain x squared divided by 2 r to a minus 3gm a cube, and a cube, well, 2 can come over here, and we have a square minus r square. This is the potential at for the points outside. Now for the point which is outside of r, of the radius r, so that is in the region 2. So now the net potential for the point P due to the entire sphere is equal to simply v1 plus v2, because this is a scalar quantity, the potential. So that is why the potentials can be directly added algebraically. And thus we have, what was the value for v1? Well, the value for v1, if you remember, is minus gm, and I think there was r squared divided by a cube. And then for this one, this is right up there, minus, it's actually plus of minus, I'm writing it directly, so plus minus of gm divided by 2a cube, a squared minus r squared. If you take a cube, 2a cube as the LCM, 2a cube, and then the 2 multiplies over there, 2r square, minus 2r square minus r square is minus 3r square, right? And minus, it's actually plus 3r square, because here you have a minus, here you have a minus, so these minus multiply to give you 3r square in positive, and minus the r square is 2r square, right? So you have minus gm, well, let's just take the minus gm outside in the first place. You have 2r square over here, and the 3 gets multiplied, minus 3, or just let's just multiply the 3 and we keep it as positive over here. 3a squared minus 3r squared. That's much simpler. So 2r square minus 3r square is simply minus r square. So this is minus gm divided by 2a cube. This is 3a square. Let's keep it first, and then minus r square. So 3a square minus r square. Now you may be wondering why we are getting such a weird result, because we could have just integrated this entire thing, that is from 0 to a, by taking a spherical shell. Well, while we are considering the spherical shell, I'm drawing it again over here. See, if we are considering a sphere over here and we consider a spherical shell, and we probably would be integrating, as you may think, we probably maybe integrating this right from the center till the very end up till here, from here to here. Well, in that case, you are missing the point of the mass consideration in case of gravity, because for a point which is lying inside, it will be influenced differently by the points or the masses that are remaining internally or internal to it, and the masses that are remaining external to it. Because all we can do is we cannot integrate the entire mass, and we cannot keep the distance the same, because the distance varies. If we are integrating it right from the center till the end, the distance is obviously varying. Their x will be varying from 0 to a. But as you know that the point is situated at a distance r from the center, which is internal now. Now in the previous case, the first one that we did, which is exactly over here, this for this external point that we did over here. Well, in this case, you can integrate it from 0 directly up to x, because the point is not internal, it is remaining outside. And with the outside point, the entire mass is being considered to be lying within that point, right? But in this case, in this second case that we did over here, the very point is internal, where we wish to obtain the gravitational potential. And for that internal point, the entire integration, as you saw over here, the entire integration will be giving the entire mass, which is exactly over here that we have obtained. This one, right? We have obtained the entire mass over here just by integrating in this fashion, right? And we could do that because it was being integrated right from the center, over here till the radius over here, right? So it was easier in that case, considering the entire mass when you are integrating over the entire radius. But here the masses are playing differently. In the second case that we have obtained over here, the masses are playing differently, means some of the masses are staying inside that point, and some of the masses are staying out of that point, in that external region too. So it was apt for us to divide those two regions, that is the region 1 and the region 2. Now, with all that done and dusted, what we wish to do further is obtain the relation between the gravitational field and the gravitational potential. Now, we have already discussed about the gravitational field, and if you remember, what we discussed is that the force due to a certain mass, so this is, I'm drawing this again, so this is a certain mass, and here we can determine its intensity, which was denoted by E. This was the gravitational field intensity due to this mass m, and let us say that there is another mass m over here. It will be influenced by this field, by the intensity of this field, and so you have g m m divided by, let's the distance, let it be r, so this is g m m divided by r squared, where g m by r square is the gravitational field intensity, which is acting on this mass m, and which is also giving us the force. So force is equal to m times of E, where E is obviously along the direction of the along which the force acts. Now, if it is being dragged, now suppose the small mass m is being dragged through a distance dr, then there will be a small work done. The work done will be simply equal to F dot dr. So that is equal to me times of dr. Now, as that happens, you are doing some work, and that work Obviously it is a negative work because it is in the opposite direction, it is in the opposite sense. So that is why what we have is simply the energy that is stored within it, and that is equal to me dot dr, because the energy is being stored in the system. If you are dragging it away supposedly, then energy, you are doing some work and your work is getting stored in it in the form of energy. So this is a minus of me dot, that is minus of f dot dr, or the negative of the work done, and this gives the potential as we defined is simply the work done per unit mass. And which mass are we dragging? We are dragging that mass small m. So all that we are left with is minus me times of, or dot product with dr, divided by m. So the m can get cancelled out, and what we are left with is du simply, or dv simply, to be equal to minus of E dot dr. And this is exactly the relation between the electric field and the potential. What we do is we simply integrate this. E dot dr is what we obtain. This is one of the relations. On the other hand, this can be put in a different way as well, where dv, because it's there, so E is simply equal to minus dv by dr. And dv by dr, v was a scalar quantity, but now it's a vector quantity with that derivative. It's actually termed as an operator, and this is simply written as the gradient operator, or the del. It is read as del operator. It's not actually the derivative, it's not even a vector, it's an operator which is operating on a scalar quantity v, and thus we, from that we have a vector quantity which is equal to the gravitational field intensity over here. So this is the same relation that you have already, have already discussed in electric field and potential. This is how they are related, and this is exactly the case in gravitation. The gravitational field and the potential can be related in the same manner as well. Now, with these information available to you, what I want you to try is that obtain the gravitational field intensity for different cases that we have just discussed. We have discussed about the um, ring, the disk, and the what was that, shell, spherical shell, and then we had discussed about the solid sphere. So with all these done, you with this relation that we have over here, this one, you can try and obtain the gravitational field intensity, because now you have the expression for potential for these things. You have obtained the potential for these things, so it will be easier by using this relation, by using this very relation. Now what I can also help you with is that d by dr, when you are terming it as an operator, this is simply I cap del by del x, that is the partial differentiation, j cap del by del y, and k cap del by del z. In case you need it that way, you can use it. So this is all for this video, and we have completed our gravitation, the portion for gravitation, and you can try these things that I've given you and send in your queries. And in case you have any queries, you can write them in the comments, or you can mail them to me, and we'll be starting off with a few numericals associated with gravitation in the numerical section. But till then, that is obviously for the upcoming videos. Till then, thank you for watching.